Now I will record to the cloud. So the topic will be the anyway, tuning of PID controllers. Which is determining the parameters of the PID controllers. Now, when we talk about the control design, our aims are, as we know, probably the most important is the stability. The system, the closed loop system should be stable, and you should have good time response. Good response, let's say, which relates to the criteria, time domain criteria, like MP, TP, TS, etc. Okay. And then the steady state error. Okay. So a good control, good feedback system is able to achieve all these goals. And I have shown you that a reasonable controller which does that, which is commonly used, is the PID proportional integral derivative type of controller, which is has three terms, Kp plus Ki over S plus KdS. This is a PID controller with parameters of Kp, Ki, and Kd. And this is a most general controller. It can be, by deleting terms or setting these terms to some of them to 0, you can have PI controller if you set Kd to 0, or PD controller if you set Ki to 0. Etc. Or if you set both of them to 0, Ki and Kd, you get a P controller. So it is possible to have different kinds of controllers. But this is a most general structure which is commonly used in the industry. Many controllers we have are of PID type or things similar to this. There are many reasons for that. They are simple. They are easily implemented. You can implement them on either electronically or using computer algorithms, which we do nowadays. So you can simply program them on an Arduino. And actually, there are already programs for Arduino. But the problem remains this: how to determine these parameters, Kp, Ki, and Kd. This problem is called the tuning problem. That is controller tuning, how to determine the parameters for a specific system. If you have a specific closed loop system, how do you determine those parameters? Depending on your system you have at hand, these parameters are going to change. Okay. For example, for a temperature control system, you will have a certain number of certain parameters which have certain values. For some other pressure control system, you will have another one. For a velocity control system, you'll have another one. So you have to determine them depending on the system. So you have to tune these parameters, and to tune them, there are two ways. You can either do the mathematical modeling, get the G of S, etc. But this is not very easy, and it requires a lot of mathematics. This is sort of hard to do, and not very reliable. The second possibility is if you have the real system at hand, do experiments on the real system. And this is easier, I suppose. So we usually select this one. So if you have a real system at hand, a temperature control system, you do a simple experiment on it, and from there, you try to determine the system parameters. And this was first done by two engineers called Ziegler and Nichols in 1942, which says optimum settings for automatic controllers. They have a paper. So they decided to obtain the parameters of the PID control system. We will also do this on our DC motor control experiment in 320. And after this, there are many others who have done similar experiments and refined those results of Ziegler and Nichols. But as a baseline, the Ziegler and Nichols thing is quite useful. Now, what do we have? We have the following feedback system. Let's say C of S. You might have a disturbance, but it doesn't matter that much. Okay, let's have a disturbance, W. This is the process. By the way, this is usually used for chemical processes, the Ziegler-Nichols settings, process systems. So you have the controller and the process, as we see. So what we do is, this is a feedback system. You do an experiment on the system. That is, you put the system in closed loop control. In the closed loop control, you just set the controller to a simple gain. So it is a P control only. So what happens is, under P control, if you increase the gain of the controller, eventually your system output is going to becomes oscillatory. That is, increase K until, let's say, Y of S becomes and even if you increase it even more, system becomes unstable. Okay, that is very typical in usual systems, in real systems. If you increase the controller gain, the system response first becomes oscillatory, then it becomes unstable. So the response will look like, if you increase the gain, you will have a response like this. You have oscillations in the system. Okay, this is Y of T versus T. As you see, you have sustained oscillations. And if you increase the gain even more, these oscillations will become unstable. Okay, so this value at which the system response becomes oscillatory is called this value of gain is called the ultimate gain. This is a parameter which we will be using. There is another parameter. You look at the response and you look at the period of these oscillations. The period of these oscillations are called TU, and TU is the period of these oscillations are called the ultimate period. Okay. So you make an experiment on the system, slowly increase the gain of the system, and system is going to start oscillating. You will see after a while. Okay. So it is only P control, that is Ki and Kd terms are 0 in this case. So using Ku and Tu, these two parameters, we can now determine the PID parameters. These are the things we will be using. Okay. Let me just a second. Okay. Maybe I should. Okay, let me try. Now there is a table which gives you the PID parameters like this, which I copied from somewhere. I'll put it here. So the Ziegler-Nichols settings are determined experimentally and empirically. That is, there is no background to them except for making many experiments. They have done many experiments on real systems and have come up with these results. If you have a controller of P-type, PI type, or PID type, you set these parameters as follows. For a P-type, you set, for example, the gain, the controller gain, to be half of the ultimate gain. Okay, and the K and KD are 0; they are not used. Okay, if you have a PI type, you set the gains to be 0.45 and 0.45 KU, and KI will be 0.54 KU divided by KU. How, why? These are, as I said, are empirical. There is no justification for them other than that they work. Okay. And then for the PID controller, they set KP to 0.6 KU, KI to 1.2 KU over TU, and KD to 3 KU TU over 40. This is how you set your PID controller. By the way, another way of representing the PID controller, as I have told you before the last time, was as follows, not this one. C of S is equal to KP 1 plus 1 over TIS plus. Okay. So this is KP is the proportional gain again. TI is the integral time. TD is the derivative time. Obviously, these two things are related. KP plus KI over S plus, this is the form I am using. And as you see, for example, KI is equal to KP over TI, and KD is equal to TD times KP times TD, etc. Okay, these two, K, this is KD. So these are related. Actually, this is another form, another representation, but actually this is more common, okay? More commonly used in the industry for some reason. But at this point, I will be using more common. I will be using this one, okay? Because it's kind of simpler. So you get the parameters, and then you make your system work with these parameters. As I said, these things work usually better with process systems, which have overdamped responses. They might not work very well with vibratory systems, but for those systems, we have other kinds of controller designs. If you have systems with high resonances and so on, this might not work. So I'll give you an example and illustrated it with Octave actually. So we have a PID controller. We have a disturbance also on the system W. Now, this will be our plant. I will be using 1 over S plus 1 cubed. It's a third order system. I think I have used this for stability before. This is why, yes. This is the response. So this is the etc. Okay. So you have a PID controller. So we have this system. So determine Kp, Ki, Kd. That's our task. First of all, let's stop this and let's share our screen. You see the Octave, right?
Yes, hocam.
Yes, hocam.
Okay, actually I have done this by myself. So the G is the system transfer function, which is 1 over S plus 1 cubed, as you see. S cubed plus 3S squared plus 3S plus 1 is G. So as you see, S plus 1 over S plus 1 cubed is here. Now for PID, we first start with the controller, which is only of P type. So do we have a K here? No, we don't have a K. But let's start with something. Let's say so we start with K equals 1, okay? And then we say that T equals, let's say, feedback of GK, G times K, and 1. Then we look at the step response of this thing. Well, it won't be, first of all, there will be steady state there, but doesn't matter. It's not oscillatory. As you will see, as I increase the K value, K, let's make it 4, the system response is going to get oscillatory, more oscillatory. Well, it is oscillatory, but still not enough. I will increase it more. Let's make it, let's say 7. So that we will look at the step response. It's quite oscillatory and it takes a long time to settle. But actually, if I make it exactly equal to 8, which I can determine from the root criterion also, the system response is indeed going to become oscillatory with sustained oscillations. Well, I have to do it for a long time. Let's say 50. Okay, now we have real oscillations, as you see. System response has sustained oscillations. We are in the limit of stability here. Okay, when K is equal to 8, anything more than 8 will make the system unstable. So for this system, by making an experiment like this, the ultimate gain is is 8. Okay, ultimate gain is 8. Then we find the ultimate period. Ultimate period is the value between those two peaks. Let's say the peak here is 16.5 as we see at the bottom. Okay, here we see here at the bottom. Let's say this is 16 point something like that, 16.6. Okay, and the other peak is at time equals 20.6 or something like that, approximately 20.5. Actually, it's 3.9, but approximately we can take the period to be 4 seconds. Okay, so the period of ultimate oscillations is 4 seconds, as you see over here. When the system responds like this with oscillations, the period, the time between the two peaks is 4. We will use this in order to determine our controller gains.
Hocam, I'm sorry to disrupt you. How we manage the ultimate gain as 8? Like, if we try 9 and 10, and like if we like increase the value of k, can we obtain bigger values?
Well, let's try to see. Let's make it k9. This is what you get. It is unstable. The response is unstable. You see, when k is 9.
Okay, hocam.
Okay. Actually, you can also find it from, root criterion. It's not that difficult. Your characteristic polynomial is p of s is s cubed plus 3s squared plus 3s plus 1 plus k, if you do it for the closed loop system. Okay. And if you write your root array, there is something wrong with this pen. It is 1, 3, 3, 1 plus k, okay, 1 plus k. So negative determinant, 9 minus 3 times, no, and then what do we have? 1 plus k. So these should all be greater than 0. Now 8 minus k should be greater than 0, which should mean that k should be less than 8. And here k should be greater than 1, minus 1. So minus 1 less than k less than 8 is the, but k should be less than 8 for stability. And that's what we found in our simulation as well. Okay?
Okay, hocam, thank you. So it is actually bigger and equal, right?
Yes, it can be equal, but it's the 8 is the limit. When it is bigger, it's unstable.
Okay, hocam. Thank you so much.
So we have found the. Let me just save it. Let's paste it here. So we want to find our Kp, Ki, and Kd values. So for P control, Kp is equal to half of Ku, which is 4. Okay. For PI control, Kp is 0.45 times Ku. 0.45 times Ku, which is 8, will give you 3.6. Okay, and Ki is 0.54 times 8 over 4, which is 1.12, I guess. 1.08, I'm sorry. And for PID control, if you want to use PID, Kp is 0.6 times. This is like this. I cannot write. Kp equals 0.6 Ku is 4.8. Ki is 1.2 Ku over Tu, which gives you 2.4. And Kd is 3 Ku Tu, 3 times 8 times 4 divided by 40. Again, you get 2.4 for some reason. Okay. So we will just simulate these. The first one is easy. So we will look at the P control only. So K is, we will say 4. And then we will look at the feedback system with 4. This. Maybe the response is here. It is kind of, not okay actually. It is, first of all, there is steady state error. It eventually settles at 0.8. We are looking at, by the way, at reference input. It settles at 0.8, which is, you get a steady state error of 0.2, plus there are too much oscillations and it settles around in 30 seconds, let's say, or 25 seconds. So it is not too good a response. You would like it to be better in two respects, both in steady state error and in oscillations. You want to have less oscillations. So we can get rid of the steady state error by using PI control. PI control means C of S equals Kp over Ki over S plus Ki over S, which you can write as Kps plus Ki over S. Okay. So I will go to MATLAB again and write C of S. C equals transfer function of, the numerator of it is Kp, which is 3.6, as we have found, 1.08 is the numerator, and the denominator is S, which is 10. So this is the controller transfer function. Now our closed loop system is G times C, feedback of GC and 1. This is our closed loop system. It's a fourth order system. So if you look at the step response of T, you can see that. Your system now has no steady state error, definitely. It settles at 1. That's good. But the oscillations have increased even more. You see the maximum overshoot is almost 50%, which is not really tolerable. Plus it settles now in 40 seconds or something. It's really bad. Okay, this is not what we want. So we go to PID control. PID adds damping. D term adds damping. PID control is C of S equals. If you do it, you will get something like this. KD S squared plus KPS plus KI, I think. Okay. So I will enter these parameters, and these parameters are here: 4.8, 2.4, 2.4. So it will be 2.4, 4.8, 2.4. Okay. Go to Octave again. So C equals transfer function of 2.4. So this is the PID controller with our tuning. Okay. Again, we do the feedback, and we look at the step response. Okay. First of all, we will note the following. This is the PID response. PID response, it is much better than PI in the first place. First of all, it has no steady state error, and it settles in 10 seconds instead of 40 seconds. It's much faster. Plus, now the overshoot is like 30%, which is kind of high, but these actually, the PID settings are optimized not for these Ziegler-Nichols settings are not optimized for reference tracking, but rather for disturbance rejection. Okay, so let's look at the disturbance rejection characteristics. TW will be the feedback of G and C, as you might remember. Okay, this is the disturbance transfer. TW is the disturbance transfer function of your system. So if you look at the step of TW, what you get is going to be something like this. Now, the disturbance response of your system will be, it will go up and eventually it will come down, and it will come down very quickly, by the way. Again, in 10 seconds, it will reject the system is going to reject your disturbance. As a matter of fact, you can even plot both the reference following and disturbance rejection together, which will give you the following result. The blue line is the reference tracking, and the red line is the disturbance rejection. And the disturbance rejection characteristic of the system is quite good. Actually, I can even okay. Yeah.
Hocam, if we get yani Türkçe sorsam olur mu hocam?
Olur.
The settling time'ı daha uzun ama yine birde settle eden bir şeyde steady state gain'i yine birde biten bir PID bulsaydık ama PI'ye göre daha uzun bir settling time olsaydı PI'yi mi seçerdik kullanmak için?
No, no. Well, you see, the derivative term, D term, always adds damping to the system. It makes the system respond faster, plus with less oscillations.
Hmm.
Okay?
So it
PI
is
control is usually sometimes used, you don't use derivative terms when there is a lot of noise on the system. Certain measurements might be very noisy, like pressure measurements or so, in which case the derivative action increases that noise and makes the system behave worse. So in these cases, you try not to use derivative action.
Mhm.
But for example, in cases like temperature control, where you have little noise on the system, you usually use the derivative term.
Okay, okay, hocam.
And also for mechanical systems, derivative term adds damping to the system, which is usually desirable. Okay?
Okay, okay,
But
hocam.
in terms of controls, that is.
Hocam, and also may I ask, we choose the steady state gain as 1, like we said, there is error when we get 0.8,
Steady
because
state gain is not 1. We give a input of 1, and we get eventually the output reaches to 1. Okay. If we have given an input of 2, the output would reach to 2. The steady state gain of our system is not 1.
so we choose R as 1 in this question.
R is 1, yes.
Okay, hocam.
Well, the steady state gain also of the closed loop system also happens to be 1, by the way, but we don't choose it. That's, you know, feedback systems usually have a steady state gain of 1 because eventually you want Y to be equal to R, as you see. Okay. So at the steady state, if you want Y to be equal to R, your steady state gain should be 1.
Okay, hocam. Thank you so much.
Okay, I guess that's all for today. Okay, if you don't have any questions, I'll stop.
Hocam, I have a question.
Okay.
Will there be a problem set 5 for the upcoming midterm, or is it a problem?